Okay, so I think we can start. So good morning to everybody. So today we have the pleasure to have Leticia Cugliandolo, that is professor at Sorbonne Université. So Leticia is a statistical physicist that has worked on many things and has given fundamental contribution to many topics, including, just to set a few, the dynamics of spin glasses, quantum spin glasses, and today she's going to tell us about Hamiltonian dynamics of classical integrable models.
Thank you, Pier Francesco. So yeah, I'm going to tell you about work we have been doing during the last 4 or 5 years, more or less, in collaboration with all these people here. So Damian was my former PhD student, Alessandro Tartaglia as well, working with Marco Picco and myself, and the group of Lozano in Buenos Aires, some new results I'm not going to tell you about today, but that we are developing with Rafael, who's my postdoc now. So before entering into the field of the talk, let me tell you that I'm chief editor nowadays of Journal of Statistical Mechanics and Theory and Experiment. So I just suggest you to consider submitting your papers to this journal. It's a journal, non-profit, free of charge, open access, is the cousin or the sister or the brother, let's say, of JHEP, for those of you who are in high energy physics. So what's the topic of my talk today? So I'm going to tell you about statistical physics of integrable systems. You will see that the motivation for doing the kind of calculations I'm going to tell you about actually comes from studies in quantum systems, atomic physics, that people have been doing over the last 10 or 15 years that have triggered the idea of going back to thinking about thermalization in classical closed systems, which can be non-trivial. So some of the questions that we want to try to give an answer to is, which is the stationary measure that describes non-pathological observables of large systems in the long times limit, when those systems have some special features, like, for example, being integrable. And as I said, I mean, there is sort of a quantum renaissance of this question. Of course, this is the ergodic question, also known for, I don't know, more than 100 years in the classical context, but it has come back from experiments and studies in quantum systems that I will recall very briefly. And what I'm going to do is talk about a very simple model, which is a variation of a model we know very well in the context of disordered systems, spin glasses and so on, that can be made integrable, and actually was known very well to be integrable, as you will see, for which we can do all the calculations, and we can take all the analysis until the end and test what is called the generalized Gibbs ensemble hypothesis. So let me start from the beginning. For those of you who are not into statistical physics and have studied this long ago, let me remind you that an important feature of statistical physics is that you don't have to solve the evolution. So let me be classical. So you don't have to solve Newton equations for all your couple variables constituting your macroscopic system, but you can estimate averages of relevant observables through a pure static calculation where, okay, you have your observable to average, and then you average it over some measure, and this measure depends on the conditions under which you're working, so isolation or coupling to a bath, and so on and so forth. And the idea is that the time averages should coincide with this statistical average, and this is what I'm going to call the ergodic hypothesis here. So, of course, the kind of measure that you have to use, as I said, depends on the conditions. So if you are under complete isolation, we use microcanonical ensemble, defined this way, from which you can define entropy, temperature, and make averages. And instead, if you focus on a selected piece of the whole isolated system, then you use the canonical measure of Gibbs and Boltzmann as the exponential of minus beta, the Hamiltonian of your system, the one that you have selected to look at. With these, you can do lots of things, like understand the origin of temperature, derive phase diagrams, understand the phases, and so on and so forth. But there are many cases, many systems that don't reach the conditions under which that ergodic hypothesis applies, and time averages can be computed as statistical averages, and so on and so forth. And some of the cases, of course, are cases where the equilibration time goes so fast and so, grows so much that you cannot reach it in an experiment or a numerical simulation. There's the case of driven systems where you inject energy. There's the case of integrability. And what I'm going to do the rest of the talk is to focus on these cases here and try to understand, whether in the long time limit there is some kind of a stationary measure that appears to describe the averages, time averages of relevant observables without making all the dynamical calculations, say. So why look at this question? As I said, there is a sort of quantum renaissance of the question, which has been motivated by experiments, particularly in cold atom systems, and simultaneously by calculations using field theoretical methods and also a lot of numerical simulations. So one of the examples where this question has posed is this so-called quantum Newton's cradle experiment, where a set of atoms of some kind had been prepared, for example, at the center of this kind of harmonic trap. And initially they had been divided in some special, some techniques into clouds, say, and let evolve. And they will separate, come back, separate, come back. And what these people have found is that this comeback was coming back to the same initial distribution of atoms quite without change. So the system was sort of coming back with oscillations to its initial configuration, that there was no loss of atoms, not important loss of atoms, and not so much of a change in the distribution that was found initially, that was injected initially. Of course, in this picture, you see that the clouds change a little bit, because a little bit there is, but it had the coherence of this problem could be kept for very, very long, and no equilibration to Boltzmann-like density operator or density matrix was observed in this experiment. So this triggered, of course, a lot of studies, and simultaneously, as I said, there were the Calabresi and Cardi calculations that were showing similar behavior for some model systems. So many others followed, of course, and there's a whole lot of literature around this kind of problem in the quantum literature. And in this context, these kind of generalized measures were introduced, and I will just define them a little bit later in my talk, these generalized Gibbs ensemble distributions, when I will tell you how it comes about in the classical problem, which is sort of easier to understand and where we can do all our calculations. And it's a non-trivial problem, as you will see. So our approach was to say, okay, let me try to reproduce this idea that I initialize my system in some way, I let it evolve under Newton dynamics, and then I see whether it reaches some kind of state that is not Boltzmann. And to do that, and to have a non-trivial situation, I have to choose some problem that doesn't equilibrate to Boltzmann. So because of that, we used an integrable system of classical mechanics. So take a classical mechanical system, initialize it in configurations chosen in some way. So for example, we chose them to be distributed with a Gibbs Boltzmann distribution. So this is like saying, I have my mechanical problem, I couple it to an environment, I let it evolve with the contact with the environment, and then I will switch off the coupling to the environment and see how it evolves further on from these initial conditions under isolated conditions, so in isolation. Of course, other choices of initial configurations are possible, but this is handy, and you will see why, and it has a lot of interesting features already in the kind of problem that we will look at. So this is also the kind of initial states that people have investigated in the quantum context. So in the quantum context, people have used initial states that were, for example, ground states of a given Hamiltonian, H0 here. This would correspond to taking beta naught to infinity, for example. But they have also considered initial states which were mixed, and they were, for example, given by a density operator of this kind. Okay? So this is just sort of reproducing what has been done quantum mechanically. And the idea is to evolve it in isolation with Newton dynamics, as I said, with another Hamiltonian H, different from the one that you used to build your initial conditions. Why so? Because if you evolve with Newton dynamics a distribution of initial conditions which are Boltzmann distributed, you will remain in this Boltzmann distribution later on. So there will not be any change, particular change in the configurations of the systems in probability. So you have to do something to it, kick it in some way, those initial conditions, and this is done by changing the Hamiltonian. And this is equivalent to what in the quantum literature is called a quantum quench. People call it a quantum quench. You change the Hamiltonian at a given instant, instantaneously, and then you see how the state that you prepared evolves further on in time. Okay? So this is the same. And as I said, I mean, if you evolve in isolation, it's like switching off the coupling to the thermal bath that you use to build these initial configurations here. Okay? And this you do at an initial time that I'm going to call 0 by convention, and that's the initial time for the evolution of the configurations. So the questions that one would like to ask is, does a large system, so I need to have some sort of large number limit to say something about statistics, right? So it needs to make the problem non-trivial and to have the possibility of developing some kind of a statistical description, the number of degrees of freedom has to be very large. So I'm going to consider an n going to infinity with n number of degrees of freedom of the system going to infinity limit, and then ask whether the evolution of the isolated problem reaches a microcanonical measure or not. Do some observables behave as canonical ones, the normal ones, the all ergodicity issue, or not? And if not, for example, for those integrable models I want to study, other kinds of measures, generalizations of the Boltzmann one that describe the long time limit of the evolution. So, as I told you, to work with a non-trivial problem, I want to work with an integrable problem. So, in non-integrable cases, there are a few constants of motion. So imagine, for example, a typical case, you only have energy, which is conserved if you evolve in isolation a number of particles. So that would be like n and energy here, just one. You could also have linear momentum, you could have angular momentum, but you typically have a few. Finite number of constants of motion. And then statistical mechanics, the usual one, tells you that the evolution of your system is, in the long time limit, described by a microcanonical measure, where what you do is that these constants of motion are fixed by the initial conditions, and these calligraphic eyes are given by the initial conditions and tell you the values that these constants of motion will keep all along the evolution. Okay, so typically it's just energy, but it could be a few other ones. In an integrable system, what you have is that you have n, capital N, number of degrees of freedom that are constants of motion. So, sorry, I should have said functions of the phase space variables and in number of capital N that are conserved by the Newton dynamics. So, if you do the isolated evolution of such a problem, what you think that you should have is that the microcanonical extension of the one above should be one where you fix all these I mu's, n of them, to take the values that they have in the initial conditions. And this has been discussed in a very nice paper in like 5 years ago, more or less, 6 years ago. And this is the case. It can be proven. For Newton dynamics, the relevance of this microcanonical extension, where you consider all the constants of motion, has been proven to be the correct description of the long-term dynamics of these integrable problems. But usually when you do calculations in statistical physics, you don't work with a microcanonical ensemble because it's difficult to handle, it's difficult to do calculations with it. Typically, what you do is you focus on some observables, some sub-parts of the system, of your isolated system, and you work with a canonical measure describing it. So can one do something similar for the integrable cases and go from this extension of microcanonical to an extension of the canonical? And this is what it is, this generalized Gibbs ensemble that people have proposed to take the form of the exponential of the sum over the capital N constants of motion multiplied by Lagrange multipliers that extend the notion of beta. So remember that normally in canonical situations you have beta associated to energy, chemical potential associated to the number of particles, if you allow for exchanges in particles, and so on and so forth. So here what people have proposed is that the generalization of that is to consider here a sum over capital N things, where you put, Lagrange multipliers multiplying these functions of the phase space variables, which are the ones which are conserved in isolation. So the question is, are local observables that you want to look at in some part of your system be described in the long time limit by a distribution of this kind? So let's try to check this hypothesis then in a non-trivial, solvable integral model. So what do I mean by this? I will take a classical integral model. It will be solvable and it will be non-trivial. What do I mean by non-trivial? I mean that it will not just be harmonic oscillators. So the hypothesis that I told you before, this, if you just have independent harmonic oscillators, it's very easy to show that it works. But what you want to do is to have some problem where you have interactions, you have some non-trivial dynamics. You may also have phase transitions, as you will see, and that in all the phases of this phase diagram that we will construct, there will be a generalized Gibbs ensemble that will describe the long time limit of the local observables. It turns out that, as you will see, the model that I will talk about has a curious relation with these other systems. And, well, curious, I don't know if it's a good adjective, but it happens to be a problem that belongs to the class of these other systems that we know very well how to study. So the idea then, as I said, is not to work with just harmonic oscillators, but something more interesting, with an interesting phase diagram. The phase diagram will be determined by the choice of initial conditions, by the choice of the quenches that we will do, by changing the Hamiltonian, as you will see. And we will be able to solve the dynamics after those quenches, build the generalized Gibbs ensemble distribution, and compute with it averages, and then compare what you get from the time averages here to the statistical average over there, and see that they coincide. So it's not trivial, and it's an interacting problem with a non-trivial phase transition, as I said, that it's solvable. So which is this problem? It's very simple to state. Imagine that you have a sphere, and that you have a classical particle on the sphere. The sphere in the picture here is three-dimensional, or is, if you wish, is embedded in a three-dimensional space. But I will take the number of dimensions to infinity in my calculations. So the number of dimensions will be this capital N I was telling you about beforehand. So mu from 1 to n label the coordinates in this space. And since the particle is not able to leave the sphere, there will be a constraint on the position of the particle that is just this one here. So this states that the radius of my sphere is the square root of n. And why do I choose it this way? Because in the large n limit that I will take in my calculations, this is a non-trivial limit that gives interesting results. And there will be another constraint, which is that the particle doesn't leave the sphere. So this could be thought about as a secondary kind of constraint that makes the momentum, if you wish, or the velocity of the particle be perpendicular to the position, and then the particle doesn't leave the sphere. Okay, if it's a free particle on the sphere, well, it's too trivial. Let's make it a little bit more complicated and add some potential energy to that particle. So the potential energy that we choose is harmonic. So there's different spring constants in each of the directions of the space, on each of the Cartesian directions. So lambda mu are those spring constants. I will order them for convenience in such a way that mu, the index, goes from 1 to n, and that the lambda n is the maximal one, is the one that takes the maximal absolute value. And again, this is a choice that allows me to do calculations analytically more or less until the end. I will choose those lambda n's to be taken from a Wigner semicircle law. This is not restrictive, it's just, it makes calculations possible analytically, while if I chose something else, I won't be able to do certain integrals, right? So there are certain nice properties of this distribution that allows me to do some integrals. Now, what is certainly important is that there is an edge, that there is a maximal value of this lambda n And it's also important that there is level repulsion in the sense that, you see, I put a smaller here and not smaller and equal. So these lambdas are different, one from each other. Otherwise, there are some divergences which are a little bit difficult to control. And that they are ordered in such a way that the lambda n I situate there. And I normalize things in such a way that the maximal value is equal to 2. Okay, that's just not very important. So my problem now has kinetic energy of the normal kind. It has potential energy of this kind. And then there is this other term here, which is a constraint. So with this term here, what I'm doing is that I'm imposing the constraint that the particle doesn't leave the sphere. So Z is a Lagrange multiplier that imposes the spherical constraint. And one can derive relatively easily, which is the expression that Z has to satisfy so as the particle remains on the sphere. And what turns out is that Z will be a function of the momentum and the position of the particle, actually a quadratic function of both, so that this last term here is quartic in the phase space variables. So in the end, the whole Hamiltonian that you have with kinetic plus potential energy plus the constraint is quartic in the phase space variables, and hence is not just, you know, quadratic and harmonic. It's more than harmonic. So this problem has been studied and proposed many years ago by, where did I put it? By Neumann, the one of the boundary conditions. You see, in this paper here from Krell in like 200 years ago, more or less. So what he was studying was just that, Newton dynamics on a sphere and their anisotropic harmonic potential with the spring constants which are different, and he was solving it for finite values of n, 2, 3, and so on. And the funny thing is that I will tell you, I was working on this problem with my colleagues, and I suspected that it was integral, but I didn't know it. And I gave an informal talk in my lab, and there was Olivier Babelon who was there, and he said, "This is Neumann's model." I said, "Okay, you know, I didn't know this paper nor the model," and then okay, a lot of hints from the literature could be used, which were very, very useful. Okay, so for this model, the constants of motion are known, and they were built by Karen Uhlenbeck in the 80s, and they take this form here. So you see they're a little bit like generalizations of angular momentum, where the spring constants appear here in the denominators, and they're n of these functions of positions and momenta that if you compute the Newton evolution of this problem, you will see that they are conserved by the dynamics. And there were many studies by Olivier and collaborators in the 90s who studied these concepts of motions in the finite n case, which was the one that was of interest to them, of course. But to me, what I want to do is I do some kind of thermodynamic limit. So I want to study this problem for n going to infinity, and as I said already, draw the spring constants from this Wigner distribution. Now, I told you that I was going to choose the initial conditions for my dynamics from a Boltzmann distribution because it's Gandhi, and it's already very interesting. Why so? Because we know from the studies in disordered systems that this problem, the equilibrium properties of this exact model in equilibrium a la Boltzmann at a temperature T0 undergoes a phase transition. And what is this phase transition? I will call it a phase transition between a condensed and an extended phase, because there is an analogy with Bose-Einstein condensation that was put forward by these people here in the 70s and studied in much more detail more recently. So the transition is very easy to understand. What happens is that if the temperature that you use to draw the initial conditions is below a critical value, basically the particle sits on the North Pole. So what is better for it, from the statistical point of view, is to be close to the North Pole. So the direction with the maximum lambda, the direction in which the spring constant takes its maximal value. So the initial conditions are distributed around this North Pole, but how much they deviate from it depends on T0, but basically they're there. So you can think about them just sitting on the North Pole, and this is why we call them condensed. So basically there is one component, the nth one, of the Cartesian basis that takes a weight which is proportional to n. And then there is the other phase, the high temperature phase, where I call it extended, where basically the particle is anywhere on the sphere. I mean, it's delocalized, it can be anywhere, and all the components have a projection, which is, so the position of the vector has a projection on any component which is of order 1. Okay, so as I said, this is a phase transition which is very well known, and with choices of initial conditions here or there, I may expect the dynamics to be different, and it will. Now I have to do a quench. How do I do the quench? I want to change the Hamiltonian with which I do my evolution. The simplest choice one can think of is to rescale the lambdas. Of course, I could do many other things, but this is the simplest one, and again, it's something that is commonly done in the quantum context to rescale some parameter. In the Hamiltonian, here I have n parameters, I rescale them all with the same prefactor of a change, which I call j over j naught. And by doing this change, basically what I do is either inject or I extract energy from my sample. Okay, so the change is instantaneous, so the position of the particle doesn't change, the velocity of the particles doesn't change either by this change, but the energy will change because the parameter in the Hamiltonian has changed. So one can see that, depending on the prefactor being smaller or larger than 1, one is injecting or extracting energy from the sample. So with these basic ideas, one can start thinking that there might be a non-trivial phase diagram for the evolution of this problem, where in one axis I put what do I do in the quench, whether I inject or I extract energy, and in the other axis I consider the different initial conditions, so condensed or extended. Okay? And then there might be, I don't know, this is just guides to the eye to start thinking about the possibilities of there being phase transitions here and there or not. As I told you before, if I don't do anything, I remain in Boltzmann equilibrium. So along this dashed vertical line, I know that the distribution will remain distributed as in Boltzmann with the same beta naught that I had at the beginning. But if I move away from this vertical axis, well, something may change. Okay. So the next step is to solve the dynamics after the quench. As I said, build a generalized Gibbs ensemble and try to prove whether the asymptotic limit of local observables is captured by that. So how do we do it? I'm not going to give you all the details, but to give you some keywords, let me tell you that this problem is amenable to be studied with what we call dynamic mean field theory or Schwinger-Dyson equations. Basically, what you can do is to write closed equations that couple correlation functions and linear response functions. So this is the correlation of the position at a given time with the position at another time. So two-time correlations. And this is how the system responds to a little kick that you may give to your particle at a given instant, how the trajectory is changed because of the kick that you give. And with these two quantities, linear response and correlation function, and how they behave in the long time limit that you can characterize with this dynamic mean field theory, which is exact in the n going to infinity limit, but not for finite n, but we are going to just focus on n going to infinity here, you can start seeing that there are regions in this phase diagram where the asymptotic values of these quantities differ. So the simplest to understand is the correlation function. So say that I start, for example, here from condensed initial conditions. So I start from the North Pole, and I evolve my system with a different Hamiltonian from the one I had to build those initial conditions. In all this gray region, what happens is that the system remains close to the North Pole. It moves a little bit, but not that much. So it doesn't decondense, it doesn't uncondense, it remains there, and this can be seen by the fact that the correlation between what happens at long times and the position at the initial time takes a finite value. So it remains close to the initial condition. Here, instead, you're injecting so much energy that you give it such a kick that you take it away from the North Pole and you make it move around. Here it was everywhere on the sphere, and you inject energy, it still moves around on the sphere. And here, in this orange region over there, what the system would like to do is to go to the North Pole. But it takes so long that it doesn't manage in the end going to infinity limit. So here it does, the particle was somewhere else. It starts moving towards the North Pole, but in the larger limit, it doesn't have the time to orient in this particular direction completely. And this you can characterize, as I say, by the limits of this correlation with the initial condition or linear response function, and you see that they take different values in different regions. So you identify this phase transition, the diagonal one, and this other phase transition, and then there will be another phase transition over there in a second. So what I said with words is this interpretation that how the particle moves from the North Pole elsewhere, or from the North Pole to the North Pole, or elsewhere to the North Pole, and so on and so forth. Now, I want to look at something a little bit more local. This correlation function and linear response were summed over all the modes, all the directions in my Cartesian system of coordinates. So I want to look at something more local. And how do I look at something more local? By looking in certain particular directions, for example, on the North Pole, on the Cartesian basis. So this problem can also be studied, for example, with techniques by John Cardy and collaborators, which are similar to what are called parametric oscillators in the dynamical systems literature, and so on and so forth. So basically what you can do is you can write just the Newton equation. This is the Newton equation. And you can plug in an ansatz for the solution, which is some kind of variation on the harmonic ansatz, or the harmonic solution. But the problem is not harmonic because of the z. So you have to play with these parameters here. It's possible to find equations for these generalized time-dependent frequencies. Anyway, I jump over the details. The fact is that one can solve this coupled system of equations for n finite now, large but finite. And this is numerical because otherwise it's not possible to do it analytically, but you can get information about the behavior of each of the position of the particle along each of the coordinates, and then look at time averages of these moments of this position, for example, time averages of the moments of the momentum, and so on and so forth. So we have access to those time averages. Now, is there an asymptotic, a stationary asymptotic measure that will describe those local observables as well? So how to do that? Well, you have to build the generalized Gibbs ensemble. I told you already that the proposal looks like this, but the problem is that these I mu's that appear in the exponential are quartic functions of the phase-space variables. So it will not be easy to calculate averages with this measure. It's not a harmonic measure, right? So, and I cannot do just perturbative analysis because there's no small parameter here. Anyway, so I have to deal with a measure which is quartic. And I have to deal with a measure that has n parameters, these gamma mu's here, not only beta, there's n of them. So first question is, how do we fix these gamma mu's? And to fix those gamma mu's, what the procedure tells you is that you have to consider that the values that the constants of motion take in the initial conditions, those you know because you know the initial conditions. So you can take, for example, the averages of the I mu's under the initial conditions that we have chosen, and those should be equal to the averages of the I mu's under this measure. These are conserved. If I want this measure to describe what happens in the long time limit, this cannot change. So they have to be equal. This equality has to hold for all mu's. So this is the condition that will fix the expressions for the gamma mu's for my choice of initial conditions. So I know the gammas. Okay? I know the gammas as a function of my control parameters in my phase diagram. I know the gammas as a function of the initial conditions and as a function of the kind of quench that I have done. But still, I have to make averages over this measure, which I told you, is a quartic thing. It's not that easy. But it turns out that this can be done, again, with the kind of techniques that we are used to do, to use in these other systems, decouplings, Haber-Stojanovich, large limits. taking into advantage the fact that the lambdas we took from a Wigner distribution. This also makes some tricks from random matrices enter the game. So without entering into the details, this left-hand side and this hand side can be computed. I don't write the integrable equations that we have. They look really horrible, but they're expressions that then you can put into the computer and get the expressions for them as a function of mu and as a function of the control parameters. So I have this parametric oscillator expectation solution for this. I have this calculation for that. Then we can compare. And if we compare, it turns out that it works very well. So this, for example, is in what we have called phase 1. So this is when the particle is delocalized, is when it's moving on the sphere with no much constraints, and that after the quench it remains moving around the sphere, no problem with that. So what you can do is compute this p is the momentum, p of lambda. Lambda is like the mu index. Is you trace the indexing with mu with an indexing with lambda. And let me see. So the red points are the solutions from the dynamics, which are below, for different values of n. So there's a bit of finite size effects, but not much, n 100 and 1,000. And then with gray, there is the solution of the GGE expressions for finite n that we can also work out. And then you see the finite size effects with all these fluctuations. And the blue is the analytic solution of the equations that we get for these p mu's squared under the GGE measure. And this is the solid line that you have over there. So the coincidence between the dynamics and the static calculation is very good. And then you can do the same for the positions. Sorry, I use S here notation, but it's X. So this is the different coordinates. And again, you have red, blue, and the gray results over there. And this is how the gammas look like. So these Lagrange multipliers look just at the blue curve. For example, you see that they are non-constant. They have some form as a function of the lambdas. And this is what is fixed by the initial conditions, as I said already. So you can get similar checks in the different other phases of the problem, and in all phases the agreement between the static and the dynamic calculation is very good. So the conclusion is that for this problem the GGE works fine, and it's nice because it's a non-trivial problem. It has such a non-trivial phase diagram with all these phases where the particle is doing different things, and still in each of them the coincidence is good. What changes, of course, is the expression for the gammas from one phase to the other. But in each point in phase diagram, I have a set of gammas, and for that set of gammas, you can compute the dynamics through the statics. So let me summarize a little bit what I said. What I said is that the global dynamics, global meaning that n going to infinity and just looking at averages over all the coordinates of correlations and linear responses, give us access to the phase diagram through dynamic main field theory methods. And the mode dynamics gives us access to what happens in each of the directions for this soft, I call it soft because we work with the Lagrange multiplier Neumann model. And that the same averages can be computed with this distribution a la GGE, which is the extension of the canonical measure for these integrable problems here. Let me tell you about another problem very briefly, because, this was for an integrable system that, as I told you, was known in the context of these other systems. It is known as the simplest spin-glass problem. It's actually not a spin-glass problem, but it's a problem that has been studied in the literature of these other systems for 50 years now. There are other problems in the literature of these other systems which are more interesting from the disorder systems perspective, and that are extensions of that. For those who know, this is the p=3 spherical model. It's an extension. I'm not going to define it, but just to tell you that this is not integrable. It is not integrable, and can, however, be studied with the same procedure. So you can initiate initial conditions in equilibrium at a given temperature with a given Hamiltonian, then change the Hamiltonian, do the quantum quench between inverted commas, and see what happens with the Newton evolution of this problem. And you can build a phase diagram, which is similar to the one I gave you before, with phases which are again similar to the ones I gave you before. So this could be like the one where the particle is moving around the sphere freely, or more or less freely. This is where it remains close to the North Pole, only that in this case there are many initial conditions that behave like the North Pole in a sense. And this is the region where it wants to condense, but it doesn't condense. What is new about this other problem is that you can have a property of this other system, which is called aging, even under these isolated Newtonian dynamics, and this is interesting. But apart from that, you know, the fact that they have these other three phases is very similar to the other problem. Only that here, this problem is non-integrable. So normally, in situations in which the system should reach an equilibrium stationary measure until the end, that equilibrium stationary measure should be Gibbs Boltzmann. And it is. So this is something that we also checked. So in these cases, you do reach Gibbs Boltzmann distribution here in the top, not there because of the slow dynamics of the glassiness of this problem, but this is another issue. It's related to glassiness. So I'm going to stop here. I think I gave you an overview of what we will be doing concerning Newton dynamics of these other systems, and I will stop and thank you for the invitation.
Thanks for the presentation. At the beginning of the talk, you briefly mentioned that the usual way of deriving canonical from microcanonical failed for those integrable systems. So
no, I don't know what I wrote. I don't remember what I wrote. But what I meant is that it's not so easy to do the usual derivation because let me see where I wrote it.
I think it's slightly afterwards, maybe.
Sorry.
Maybe slightly after. I'm not sure actually. Yes, there.
Yes.
At the bottom.
So what I meant is that if you look at how you derive the canonical from the microcanonical, you have to separate the system in two pieces, right? And there is somewhere where you use that the system you focus on is much smaller than the rest, because the rest is like a bath, and that you use that you have only a few things that are conserved in the whole system. So what makes the derivation of this part here is that here you have a sum over n objects. And if you want to follow the normal derivation, when you have an n that will go to infinity, it's not obvious with the scalings of the things. It may work, it may not work, I don't know, but it's not so obvious. And for example, the derivation that I have in mind is that the one that people who studied long-range interacting systems usually do. And there you will see that, because of the long-range interactions in their problem, it's not obvious to derive canonical from microcanonical. And here is because of this large n number of constants of motion that you have.
Okay. And it's...
Because you see, here the problem is that all these things should scale like an n with n. It should be extensive, not super extensive. And if you have a sum over n things, and I don't know how I use scale, there should be other one, because otherwise I have super extensivity. So there is a lot of little issues like this which are tricky.
Okay, yeah. Thanks.
Yeah, thank you for the very nice talk. I did not really understand the difference between phase, I think, 2 and 3 in your diagram. So what would be an order parameter, or what's the phase transition between them? Is it just dynamical, or?
No, you see here, if you look at what happens, for example, with the limit of the correlation with the initial condition, it goes to 0. So here you started from anywhere on the ball, and you went sufficiently far away so that the correlation is 0. So the particle moved really far away from where it was at the beginning. While here, you started from the North Pole, you moved a little bit, but you remain close to the North Pole, because this Q naught is different from 0.
So maybe I'm in between 1 and 2 then.
Okay, so 1 and 2
is purely dynamical.
Exactly. So you see, from the correlation, you don't see any difference, because it goes to 0, it goes to 0. From the linear response, you do. So this is case like Curie law, between inverted commas. This is scale like 1 over j. So the response is different. And what this response that is different is telling you, if you look at it more carefully, looking at other observables, is that here the particle is really moving towards the North Pole, but it doesn't have the time enough to reach it. I should be doing scaling of time with n to be able to really condense in this region of the phase diagram, but I'm not doing it with this calculation.
I see. So it still makes sense to talk about, I don't know, what is the order of the transition? And
Yes, yes. So they're all continuous, these transitions. Here they're all continuous, while in the other problem I talked about, there are some discontinuities.
I see.
Yeah.
Okay, thank you.
Yeah, okay.
You choose the geo ensemble for like the eigenvalues and
Yes.
everything, and usually it's related to chaotic systems. So if you choose like a distribution which is Poissonian, for example, or something like that, do you still have this kind of behaviors, or is it?
The problem with integrability is that the lambda should be different. If you have two lambdas which are equal, it's like you lose constants of motion and then you're in trouble. I mean, you don't have enough. So we chose this distribution, Wigner distribution, because I was coming from these other systems, and in that context, it was a natural one. I didn't know, as I said, that this problem was integrable from the beginning. I suspected it, but I didn't know it before, and that it existed. So the lambdas, I think that what is important is that there are no repetition, but the fact that it's Wigner or something else, I don't think it's important. So the only thing that is certainly important is that there is an edge, that you don't have tails. So if you have, lambdas that come from a Levy-like interaction matrix, then something else will happen for sure. But if you have an edge and you don't have, superposition of lambdas, I think that my results will, with the little changes, of course, the transitions may not be exactly in the same place, and quantitative changes, but not qualitative changes.
Yeah, so basically, like the distance between two eigenvalues need to have some smallest distance, which is what you engineer by
exactly.
Theory. But with Poissonian, I guess, like they can be as close as possible. So
I don't want that.
Okay.
Exactly. So I don't want them to I want that the Wigner surmise, that there are no, that there is level repulsion. Say.
Okay, thank you.
Maybe I have a question
Yes.
about the initial conditions. So, because the statement that you have about the equivalence is true in the larger limit with probability 1.
Yes.
But now I can imagine that I ask the question, can I have a large deviation such that I take a small volume of initial condition for which the statement is true? Can I make, it would be like kind of scarce.
Exactly,
like
it could be like scarce, yes. I don't know, we didn't look at it, but it could be like scarce, yes.
Okay.
Yes.
Thank you.
Yes, sir.
Okay.
Thanks. Naive question. So in your Gibbs distribution, so you take exponential minus gamma or lambda I mu, because I mu is conserved, but I mu squared is also conserved. So how do I know?
Sorry? It's I squared. Why
yes.
do I know this is one?
Yes, and not the squared or the cube.
Well, you could ask the same question with
yes.
Boltzmann, right? I could put h squared. It's also, so it's you need a set. They will most probably, if I use another version, let's say, of the I mu's, if I don't know, if I take functions of these I mu's, which are still in number n, and I put them here, the parameters that will accompany them will change, of course, but I will find the same thing. For the statement that there will be a distribution that describes.
Yeah, but that would be a different distribution, no? If I take I squared.
Yeah, it will be a different distribution, but it should also do the job of describing my asymptotic values. You could ask the same question with the normal Boltzmann. For normal Boltzmann, in microcanonical, you conserve h, but you also conserve h squared, h to the fourth. You conserve all the functions of h.
So maybe I'm completely wrong, so in this case I'm sorry, but I guess it's related to the first question. I assume when you have a thermal bath, thermal equilibrium, you can derive it. Here, if you have none of these, is it, it's not so clear to me that you know from first principles that this is the distribution you should expect, because you have plenty of amus, which I'm not sure all of them have a clear physical meaning. So it's not, I'm not sure it's clear which one I should use, you see.
If you wish, take it as a proposal. People have proposed, let's look at this, which is the most simple generalization of Boltzmann for a problem with n constants of motion. And let's put it to the test and see whether it works. It's exactly what we did. I mean, we just, propose this one and see whether it works. It does. I mean, and it does in a non-trivial problem, which is not just harmonic oscillator, so this is nice.
Okay.
You determine the gamma mu just by saying that the I mu will be constant.
Exactly. Yeah. They have to be, I don't know if you wrote it here, they have to be, in convolution to have enough, but the expressions that Uhlenbeck gave are. So they have to be independent, no? The I mu's through Poisson brackets, and they are.
There is no contradiction with the GG.
No, exactly. There is no contradiction with the GG. But it's in the quantum context, people have, there are discussions, whether it's enough, whether you miss, because you never know whether you have all the initial conditions, all the constants of motion, there were all these discussions. So this is a problem which is non-trivial, where this is working. Just that.
Other questions? Okay, thank you very much.
Thank you.